The next speaker is lining up now. It's more or less ready. It will be Pedersen that will talk about the latest news from the landings on Mars.
Do we need to go to curtains to
Maybe.
need darkness so we can see Mars? Is Mars bent or
Yeah,
right?
it's technically better.
Yeah.
It's okay.
And then you won't be able to see my red eyes. I don't think it's a reflection from the planet Mars, or just a result of some late hours of work this morning. As of now, the material from Mars amounts to several hundred pictures, and the experiments are beginning to take action, and lots of data are coming down. So I'll give you some of the news results today, and of course these are very preliminary. It's not what you would call good scientific facts as of yet. We still need some calibration and all that sort of things. And besides that, my point of view stems from an interest in the Martian meteorites, and thus the title of my short lecture today, Searching for Early Life on Mars. I'm very interested in the geological, chemical environments and the early Mars 3-4 billion years ago, and especially one Martian meteorite is good in this context, and that is Alan Hill's 84001, which you no doubt have heard about. So before I give you some of these good things, here we have the first image that we got down from Mars. It's the HazCam hazard camera on the Spirit rover that takes a little peek out and sees Mars. And actually what you see here in the background, it was immediately thought to be a big rock, but it turns out that it's one of the airbags that hasn't quite deflated yet. And the status on this is a current problem at NASA for the men working over there as well.
Oh, I thought we solved that problem after that time.
No,
Because it was the same problem.
actually not yet. Actually not yet. The status on that problem, as of now today, is that we won't be able to get off the lander till at least the 16th or the 17th January, because they're afraid that something could happen. And
You're kidding, the car's just standing there. It's
it's
going
just
to
standing there and taking pictures on the way it is. And the problem with this is that if you try to drive this way down and something happens, a wind comes by, you could imagine all sorts of things. The rover could eventually tip over.
What will happen in the meantime?
Don't they have a two lane? I mean, the Pathfinder, they had a problem with one, but then they could go down the other way.
One
But
of
they
the
only have
ways
one
to
way.
get by this problem is to turn the rover and go the other way down. And that's we work on at the very moment. But it seems like we won't get over until the 16th.
It takes 2 weeks to turn it.
But what happens in the meantime that makes it possible on the 16th to go down?
In the meantime, they are going to take all the pictures that they possibly take in the highest possible resolution and make release their
But why will it be possible then to get off?
because they're trying to lift one of the pivots. The airbag is situated partly below one of the pivots of the lander, and they're going to try to rock a little bit and see if they can get by the problem this way. And the other picture that I sent to you here on the right is my personal interests. A batch of magnetite particles, and the sizes of these particles are around 50 nanometers wide. And these particles are from the Martian meteorite Alan Hill's 84001. And in this brief 30 minutes, I'm going to try to establish some sort of connection between the two Spirit rover and the Martian meteorite for you. So that's my intent. We'll see how I manage. I just start out with the Mars Pathfinder lander from Mars 1997 and show you the magnet array on Sun 68. And one of the main results from that mission was
Maybe
that
you should say that Sol 68 is the 68th Martian
the
day.
68 Martian day, yes, of course, and it's almost the same as 68 days on Earth, but not exactly. The saturation magnetization of the dust amounted to around 4 ampere meters, square ampere meters per kilogram. And the tip plate magnet that was included on that mission would be capable of detecting if there was a single phase component in that dust. Because one of the major problems is that we do not really know what kind of magnetic mineral that causes these particles to adhere to the magnet. It could be a single phase, it could be pure magnesite, something like that, or it could be composite particles. If it's composite particles, then the next question arises will be, where is the magnetite, or where is the hematite, or where is the magnetic mineral in these particles? And are all the particles magnetic? Was it just something? That's one of the problems that came out of that mission. What we tried to look at was some signs of change down here. And as you can see, it's not really clear from the resolution of the image if there is change or not. So,
could you tell us what is it we're seeing there?
Yes, what we are seeing. You're thinking especially in the tip plate magnet. Yes. What we saw up here was basically the determination of the magnetization, saturation magnetization of the dust. And down here, if we have a single phase component, we should be able to see some sort of linear features, not just a conglomerate of dust without structure on the magnet. The construction of this magnet should cause single phase particles to align in chains that could be visible to the direct eye. And it's not really clear from this picture whether we have this phase or not. It could be a small component of the dust that is single phase. That's really interesting.
So this, it looks like that there is a block with a ring around. What does that mean?
It's a magnet with dust.
It's a magnet. And there's a strong magnetic field at the center, and then there's a field gradient. And this field gradient causes the alignment of single phase magnetic particles, but not composite particles. They will not align. And the interpretation of the experiment was ambiguous. And I'll get on with that in just a little while. Okay. Back in the early 90s, we received a sample of Hills A4001 from NASA. And we began some early studies in the early 1990s. It was not yet clear that this meteorite came from Mars. But in 1994-95, especially David Wilfeld discovered that this meteorite had been classified wrong. And thereafter, a huge interest was spent a lot of experiments with meteorite. What we have been doing at the Institute is that we have been trying to crush this meteorite and make a magnetic separate from it. And this is especially difficult because the magnetic particles in meteorite are very, very small, and there's not a lot of them. And what we wanted to do with this magnetic separator is that we wanted to take whisper spectrum, see how much we see magnetite, how much we find hematite, and so forth. And then it would be obvious to take it one step further and look at direct particles. Put them on the electron microscope and see what is the purity, the event purity of the particles, and what's the quality, and can we say anything about crystal structure and the possible origin of these particles. And there's a lot of statements here. Actually, it's partly conclusions and partly literature studies. Conclusion is in Danish. It's not really important for us, but what's important is that Hills has a complex geological history with a lot of, we call it, shock events. And one of these major shock events occurs around 4 billion years. And during this shock event, we believe that water or some other fluid, possibly water, penetrated this meteorite and perhaps brought some particles with it. One of the evidence that we see in this event is that carbonates are abundant in this meteorite. And these carbonates, they differ somewhat in morphology. Some carbonates are spherical, some carbonates are pancake-like, more flat. But a common feature of these carbonates is that they have a black rim. Some of them have a white rim as well. And in this black rim, we find the mineral magnetite. We also find some other minerals, but this magnetite has become the main field of study this meteorite for a lot of people. The origin of carbonates as well as magnetite has it's not been easy to determine. There's been a lot of arguments about hyperthermal precipitation, gas phase reactions, so we can make at very high temperature, around 600 degrees Celsius. Precipitation from solutions at low temperatures is of course the opposite arguments in many ways. And then there are a lot of alternative explanations for shock, for instance, and a biochemical mechanism. In 1996, Dave McKay and a group of other scientists from NASA published an article claiming that they had found possible fossilized remains of biological activity in this meteorite. I was careful using these words because that was really their arguments indicated that something had happened. It was possibly biological. It was the simplest explanation, but they put it out and they said, let's look at it. Let's really take a look at it. We're not actually so sure, but it's pretty strong what we have here. And they based their argument on, for instance, that the carbonates are very high with hydrocarbons, that these very small magnetite crystallites look like something we know from Earth have a biological origin, and as well as they found some bacterial-like structures in the carbonates. These arguments have been tested, of course, in the late 90s and 2001. And
People are still debating it.
yeah, people are still debating it. And you could say that the interest seems to be growing a little bit because it's actually been so difficult to either prove or disprove this argument that it's been really hard to get on with it before we have some new instrumentation. These arguments are all debated heavily today. You cannot say that some of them are invalid or especially valid. What we've been trying to do is that we have tried to find these magnetic particles. And of course, what we wanted to do was to take directly these magnetic particles off the rims of carbonates. But that is very difficult. That's a very difficult problem because the typical sizes of these carbonates are around 50 to 100 microns across. So it's not something you just grab your pictures and then you snap on these crystals and you look at it. It can be done in samples.
So you guys have a piece of it?
We have a piece of it, yes, and we are lucky that our piece contains carbonates because it's not all the pieces that's been sent around the world that are similar hydrologically to each other.
So how much do you have?
We have around 2 milligrams or so left of it. It's not really that very much, and the response pictures the same, of course, well, quite a bit of the sample. We were not so interested in what meteorite, so we crushed a lot of it to make magnetic separate, and then we spectrum from it.
But the meteorite is only quite small, it's only order of 1 kilo.
It's very small.
And everybody
it's
wants a
around,
piece of it.
it's around the size of a big potato. So it was obvious that when we had crossed it, it was not really my idea, but I think it's a great thing to do anyway. I might use some of the rest of it and see if we can do something with it. And then the answer came out, okay, electron microscopy, you can look at anything with electron microscopy. You don't really need that much. But of course, to do something that will give you some results with electron microscopy, you have to be very careful preparing your sample and getting the right piece of material from the start. That has been the big problem. I put a lot of analog materials in the microscope to try to evaluate similarities. Also because the study of minerals with electron microscopes is really trying to look at some answer. Then you say, there's one answer, then okay, everybody gets the answer. Thereby you may have some other instincts and you don't see them because you're just looking at a very little piece of the test sample.
Do you use the TM Elisa or what else?
I use the TM set, the research, mostly the DTU, and it's a really institute in Rotterdam, one in Aarhus, next to the Cardiff Systems, and biological microscope. So I put it around as the main instrument for this time. And it quickly turned out that in order to get a systematic result for this meteorite, we had to develop some sort of data analysis scheme program. And it was obvious to try to digitalize our images and then do all the analysis on the computer, because then we would have some common standard. It would not be the typical electron microscopy's problem of looking at it with your own eye. That can be very good, but if you're not that experienced in the field, you can also easily make mistakes. So doing this, we would have the advantage of a large data sample, then we could correlate between the samples, so we could adjust our own level of accuracy.
Could I just ask a question? So
Certainly.
I'm curious, when you have such minute sample sizes, don't you need to be very careful about moving it from...
Certainly.
So So how, I mean, just from a practical perspective, how do you do that? If you travel around with it from one place to the other?
One of the big questions was if we should keep the sample in a clean room facility under inert atmosphere and all that, and then minimize the time that we got it out and treat it under the same restrictions. And we did some experiments to see how much cleanness we needed. And we did these experiments from the point of sample pollution view. We did some experiments on X grids, for instance, and we did some experiments continuously on one sample to see if we could detect any impurities. And using this kind of approach, we were able to determine how we could handle the samples. And it turned out that biological contact is, of course, extremely hazardous with these materials. You should not sneeze on them, but if you handle them properly without putting them out in the rain, so you can actually transport them in closed boxes from place to place. And that's of course very important for us to do this also. Go to Aarhus, for instance. You could pick a lot of things up on the road. Yes, certainly. So we were very careful to look at a lot of samples. Around, I think we spent around 200 templates on our samples, and we have not looked at the entire meteorite certainly. So we have a lot of reference samples.
Yes. Question along the same vein. The meteorite Evan Hill was long exposed, at least the outer parts, to the Earth's atmosphere. I don't know where your sample is actually coming from, but other parts that have not, say, for example, been exposed to oxygen here, I could imagine that this might even change the chemistry of your sample.
The question of where from in this meteorite our sample steps is really an important one. And I tried to trace it back as good as has been possible. And it turns out that our part of the sample is from a special, a little bit special lithography. And you cannot actually say there's a lithography A, lithography B, but you can say that this area seems to have margin instead of earth-like carbonates, and the pollution in this part of the sample does not seem to be very important. Earth-like pollution and space-like pollution has not significantly contaminated this area. And we have done that by tracing back the position to the sample, and then other samples that other laboratories have studied in this area, so that we can say, okay, there's a neighboring sample here. And they have studied it using, for instance, mass spectroscopy or something like that, and they don't see any pollution. So it's indirect in that way. But it's a very important question.
Also another question here, so you spread all these samples out all over the world. So how is the coordination between the research groups and this type of experiments you're doing? So I assume that you're coordinating this with what other groups are looking at so that you get a picture.
Yes, we do that, but we do that primarily through literature. By reading, of course, a lot, and then by following the work of others.
But you don't have any conferences where all the people that have samples from this
There's been quite a few interesting meetings on Mars with presentations in the meteorite. But
none with a specific goal of sort of coordinating this effort.
No, Martin, we're not competing.
And I was really saying that it's a hard question why someone has not tried to coordinate.
Yeah, that sounds
It would be a very good idea. But it hasn't been done as of yet. Okay. So what came out of all this effort? After around 1.5 years of integration, thanks to pedersen, who I understand now no longer works at the School Institute, we were able to finally get a response spectrum of the magnetic separator. And this spectrum was very interesting. It was mainly of large quantities of magnetite, these peaks.
Isn't it weaker than the normal? I mean,
yes, it is.
I know you don't have zero on the bottom, but
we had a little problems because the magnetic material was not present, and that's figuring out. So we had a very thin layer of magnetic material, and also we had not crushed it completely. So it was a bit, you can call it, disorder. There would be tiny holes in our chamber, but it was reproducible. That's important. Also, we found some minor traces of pegmatite.
Can I ask which wavelengths are we looking? At which wavelengths are we looking here?
It's 14.4 kilovolts.
Okay, so
Yes.
yeah, it's the US power, so
Yes.
yeah, okay.
Okay. Then we found traces of hematite, magnetite, and also pyrrhotite. Perhaps pyrrhotite. And pyrrhotite is the least certain mineral in this sense, because this peak up here actually is very close to metallic iron. Metallic iron is not something you would expect on the surface of a planet with very oxidized environment. But so we followed it for a while, and it seemed like there is a correlation. I think we have so much in the project. And also, it's not magnetite. There's a vast amount of decisions very big use in this context. Magnetite can be released or formed by a huge number of mechanisms. Some one can release primary magnetite, of course, as well as secondary magnetite. Biological activity is very much discussed on Earth. The number of diversity of organisms. If we get a little closer in a microscopic sense to the magnetite particles and elemental constants. And here are some examples from studies of pyrrhotite materials that creates magnetite in order to align themselves to the the original material, all mineral meteor, this is a carbonate, and this granular material then is actually magnetite in a not so crystalline form. Yes, it's crystalline, but it's not actually any with there are no the way it basically says crystalline components. This is from
Earth life, the first one. I mean, it's metabolism, right? It's a byproduct of metabolism. No, by Earth bacteria, because only one.
There's really two kinds of biologically produced magnetic particles. There's the biologically controlled mineralization of BCM, and then there's the biologically induced mineralization. And the controlled mineralization takes place inside the cells. And the result of this mineralization is that long arrays or chains of magnetite particles are created, and the bacteria use these chains as little complex needles in order to align themselves to an organism. And the other sort of biologically controlled induced mineralization, BIM, is that a particle generates some kind of iron oxide or magnetite on the surface or close to its rim as a metabolism thing. And these particles are not as well crystalline, well developed as the controlled mineralization.
So it's really true that the bacteria they're using, I thought it was just that, because this is one of the most obvious metabolic, and one of the places you get most easy a lot of energy, and then it was a byproduct of metabolism. You're saying there are two different kinds. There's one where it's just byproduct, and then there's one form where the bacteria somehow use it.
Yes, you could say that I'm not so happy today that you should assume this is that. Let's say it really isn't. I think it is. But then the rim here of the particle would define some, of course, define the particle, and then it remains disordered, it could be amorphous remains, remains really of interest anymore to the particle. But the control mineralization takes place inside. When you observe the result of control mineralization, then you can actually see on very high resolution photographs that there is some sort of organic matrix that controls the formation of the magnetite. You can see that the magnetite particles, like these, they have an outer layer, some sort of organic film, and this organic film controls the formation of the next magnetite particle in the chain. The effect of this control is that the lattice planes in these magnetite particles are actually aligned particles. You would not expect to see that if you just had particles that were randomly formed, not controlled. So really, that's a very important question, and I think it's the most important criteria today for determining whether magnetite particles are really biological objects or not. So it's a question. Answers.
Okay, so I guess what you like is if you organize arrays of structures, linear structures, some kind, that would be very difficult to explain, unless it was bionic.
This is really boundary research. It's the rules for determining whether it's a biological or not are still being discussed. And it's a matter that's been mostly discussed around 2001 first. So it's very new. And the rules, which I will come back to in a few seconds, are really to those ones. But it would take several companies to have aligned disciplines in an uncontrolled growth. If we suppose that the magnetite, for instance, was created by some sort of hydrothermal mechanism, the solution actually and you would really make the things control this and you make all some particles. That explains it.
The materials can use these constructs. They live happily on Earth and they use it to orient themselves and put them in a gradient of oxygen. So the Earth bacteria for us which produce these kinds of live by respiration of oxygen. And the other thing is, so there was the whole question of contamination. Maybe this has been sitting on the ice for some time, and maybe bacteria, just Earth-like bacteria, have the emission. What you see is fossils or the remains of these Earth bacteria. And the other thing is, I thought that it has the possibility to really use an active mechanism just for just give the right conditions.
Not to put it off, but I'll get back to that in just a few. Because that's not easy.
Can I follow up since this issue there has been lines on the
it's around
16,000 years or something. 16,000 years.
Fossilization doesn't work.
Yeah, well, you have it's a single cell here, so it's not like bones to fossilize. They can still be organic molecules.
You should take the meteorite, because slices it and take some samples out from the interior. And then you find these carbonates up here. And if you look down, you find particles. And if you look carefully at these rings, then what you hope to see is something like this. If it wasn't not would it, because we just have some array of magnets and particles here, they are solidly arranged. We don't see any special signs, except if they're pure and they seem to have defects. But then look at that display is being aligned. These particles up here, we're pretty sure that the original of this question is part of geological materials, but it has been investigated using various kinds of methods that earthline contamination has not entered very far into the interior of this meteorite. And Mackay has studied these carbonates from the interior of the meteorite, where you do not expect complexity. To be very short, if you look closer on the magnetite particles from this meteor, then it turns out actually you cannot say they are biological. That's really deep into a long story short. As you can see, it's a long story. We conclude that the magnetic particles in this meteorite, mainly magnetite, there are several different types of magnetite, and these different types is really the sort of the study using reciprocity. It's because they say, okay, actually look at these particles from the rims of the carbonates, they are that you try to help them really not crystallize, because they do that in the later years. So that's a problem in this analysis. And we have not, of course, found a better answer to this very last question that was like, but we can at least say it's like to pick up magnetic dust. We have the filter magnet here, with the field gradient, and we have, to be quick, that's the same, we have the sweet magnet here, aligned very closely to the pancake calibration target in order to get two kinds of information just in one image. And these images are not publication quality. There are some diffraction effects that are being worked on, removed. But what's important is it seems like there's dust in the center of the meteor, of this magnet. Sorry. There's dust in the center of this magnet. And there really shouldn't be if all the dust is magnetic, because the center of this magnet has been designed to repel magnetic material. And we're not sure because of partly problems with the pointing of the camera. There is some sort of shadows and diffraction effects with the hand camera And therefore we are not quite sure of the colors. But it looks like that the dust may be composite in the way that all the dust particles are alike. And of course, if I not get into this, the robotic arm on the rover is capable of doing experiments e.g. by grinding and by analyzing the thermal emission and by doing whisper spectroscopy on samples. And what is just beginning is that we are doing thermal emission spectrometry on the surface. As you know, thermal emission spectroscopy allows us to detect variations in a mineralogical context. Sorry. And what we really see here is actually the surface temperature. The red areas up here are hot, and the dusty areas, and the blue areas, mainly the rocks, are the cold areas. The blue, the rocks, is what you would expect to be the coldest because they have the greatest heat allowance. They can transport heat easier from the soil. And if you analyze these color images further, then you actually find that there are minerals in the soil that contains bound water.
How did you see that from the
This is by analyzing the absorption features in the spectrum. I'm really sad that Karen couldn't be here today.
That's the spectrum of crystalline water? Or?
That's the spectrum of the bound water in the mineral. I'm a little afraid to say crystalline water.
Okay.
Because we are not certain what mineral we're looking at. And that's why I'm not very happy about telling you that it's crystalline water or something like that. It's some sort of
these are hydrous minerals.
Yes, it's hydrous minerals of some sort.
Mostly clays.
And what we are currently discussing is that this could be zeolites. It could also be gypsum. And this is important because in
That's
Adam
a
Hills,
water product, right?
right? In Adam Hills, we find anhydrite and hydrite, this is called. And this could be a gypsum-like phase. It could be a clay-like phase, probably a zeolite and an aluminum silicate phase, and it contains bound water. And the important thing about this is that we expect some sort of water to be on Mars, some sort of bound water. This has been discussed, but this is more than would be expected from the average surface of Mars. It's not a huge water content, but it's significant.
But how can you tell? I have no clue how to read this.
I'm not a spectroscopist either, but there are the wavelengths of the absorption features correlates with the sort of bonding in the mineral. And that's why you can trace it back.
It's NOH one.
Yes.
And then it would look different depending on whether it's sitting on something or it's sitting on something.
I just can't see this is a lot of water. If you told me this means that there's no water, I would say, oh yeah.
It's significant because it's a large peak, and also the camera on the rover and the orbiting camera on the Mars Global Surveyor matches. So it's pretty certain result. And the last spectrum I'm going to show you is that of carbonate. As you know, carbonate has been searched for extensively on the surface of Mars using spectroscopy, and some people claim that carbonate should exist, perhaps not be abundant, but should be a minor phase in the Martian dust, and we are beginning to find it at Kusik. And as you know, carbonate and bound water, they are two perhaps little parts of the history of water on Mars, but nevertheless two important parts. What I would like to do personally is that I would like to see the response spectrum of these carbonates to see what kind of magnetic minerals they contain. And with this, I will say that I, of course, exclude some material, but I hope you forgive me, and then we'll leave some other time to discuss, hopefully, the rest of the story, if there is one. Thank you.
I think we will go directly to the last speaker, and maybe we can discuss over the pizza if you're staying. This is good. So
maybe we should actually get try and get the pizza at this point and can eat it while.
Did you think so? Yeah.
Okay.
You want to check?
Yeah, it was 12:30, so I mean, how many pieces can we
I mean, we'll have at least a beginning and then we can...
Okay, so we will have a 2-minute break if anybody needs to in hall or out hall
Wait too long
or
with